Global Positioning System, GPS. The GPS network consists of 24 satellites, each of which makes 2 orbits around the Earth per day. Each satellite transmits a P is equal to 50 watts or even less sinusoidal electromagnetic signal at 2 frequencies, one of which is 1575.42 MHz. Assume that a satellite transmits half of its power at each frequency and that the waves travel uniformly in a downward hemisphere. Part A. What average intensity does a GPS receiver on the ground directly below the satellite receive? There is a hint. First, use Newton's laws to find the altitude of the satellite. So we have 2 orbits per day, which means there is a 12-hour period for these orbits. And the satellites perform uniform circular motion around the Earth. Uniform circular motion. So that implies the gravitational force, universal gravitational constant G times mass of the satellite, mass of the Earth divided by the radial distance squared is equal to mass times the centripetal acceleration mv squared over r. Now, v is related to the angular frequency, angular speed, omega times r, so that we have m omega square r square divided by r is the centripetal force, which is m omega square r, and omega is 2 pi divided by the period, 2 pi over t, the period. So we obtain m omega square r, the centripetal force, is equal to m times 4 pi square r divided by the period squared. Okay, now if I substitute this to the gravitational force, I will obtain G m capital M over r squared is equal to m 4 pi squared r divided by the period squared, and this will give us, for the altitude or the radial distance from the center of the Earth, to be, because the masses here will cancel, this m will get rid of this m. So the radial distance is 4 pi gm t squared, g mass of the Earth t squared, divided by 4 pi squared to the power 1/3. Now, the gravitational constant G is 6.67 times 10 to minus 11 Newton meter square divided by kilogram squared. The period of the orbital motion is 12 hours, which is equal to 12 hours, 60 minutes, 60 seconds. That is 43,200 seconds. The mass of the Earth, m, is 5.97 times 10 to 24 kilograms, and the radius of the Earth is 6,370 kilometers. So from this we can obtain the radial distance between the satellite and the center of the Earth, it is 6.67 times 10 to minus 11 gravitational constant. Mass of the Earth 5.97 times 10 to 24 kilograms, 43,200 squared divided by 4 pi squared to the power 1 over 3, and this gives us a radial distance as 2.66 times 10 to 7 meters. And we are told that these waves travel uniformly in a downward hemisphere. So this is our picture. Our satellite is at a radial distance r from the center of the Earth. So we have to subtract the radius of the Earth to find the altitude. And the electromagnetic waves move on the downward hemisphere. So the waves generated by this do not go up in the upper hemisphere, only to the downward hemisphere. So that's what we should think about. They travel uniformly in a downward hemisphere. Now, what is the altitude? H. H is equal to the radial distance r minus the radius of the Earth. So it is 2.66 times 10 to 7 meters minus 6.37 times 10 to 6 meters, radius of the Earth. So we find the altitude to be 2.02 times 10 to 7 meters. Now the intensity that will hit the receiver is the average power P divided by 2 pi h square, which is the surface area of the downward hemisphere. Now, since we have half the power per frequency, for the given frequency here, we have 25 watts. So it is 25 divided by 2 pi, 2.02 times 10 to 7 meters squared. And therefore, we find the intensity to be 9.75. Let's move this a little bit closer to the left side. 9.75 10 to minus 15 watts per meter square for each frequency. So that's the answer for each frequency. Okay, so in this part of the problem, first we calculated the radial distance between the satellite and the Earth, and that's basically an application of one of Kepler's laws, really. R cube is proportional to t square, and it comes from uniform circular motion. Gravitational force Gmm over r square is equal to mv square over r, or m omega square r, where omega is the angular speed or angular frequency, which is 2 pi divided by the period. So knowing the period is 12 hours, we know the mass of the Earth, we know the period, and we know the gravitational constant, 6.67 10 to minus 11 Newton meters square over kilogram square. Substituting the numbers, we obtain the center to center distance, 2.66 10 to 7 meters. We subtract the radius of the Earth to find the altitude. And this the problem states that the waves travel uniformly in a downward hemisphere. The waves travel uniformly in a downward hemisphere, which means we don't need to consider the full sphere, we only consider the downward hemisphere. And therefore, it's the average power, 25 watts, because the power was shared equally by two frequencies, divided by 2 pi h squared, the area of the downward surface area of the downward hemisphere, gives us the intensity for each frequency.